Hello, my name is David Beggs, and this is Project Cizin. So just really quick, for the sake of the demo, I'm going to actually start the program right now. We'll get into that later. Let's begin. So a little bit of background about this. Earthquakes are extremely difficult to detect when oncoming and impossible to predict. Most scientists really can only generate a time frame for a possible earthquake in terms of prediction, and it's usually in a time frame of years. Sensors themselves, even extremely high-end ones, produce very noisy data. The environment around a sensor, especially if it's in a city with a lot of construction, can often produce a lot of really hard to parse noise. And a basic distance threshold produces a lot of false positives. So there's a standardized equation that they use to do earthquake early warnings. These are systems that are employed in San Francisco and Japan and places that are more prone to earthquakes. And of course, depending on the epicenter of the user, these systems are very helpful. Although, as you see below, they can produce up to 30% only up to 30% true positive rate. These systems are still extremely useful. If you're in a location that is maybe in an old building or an old bridge that could potentially take structural damage and pose threat to you and your person and your belongings, that can be extremely useful. Depending upon your situation, there's a lot to be saved in terms of damage. Another thing to note is that these equations are not specialized around the locality of the sensor. So luckily, their equations are relatively resilient to this. However, it still poses some issues in terms of calculation. So just the minimal that we have to know about the geology for this project. The earthquakes are composed of two waves and some aftershocks. The first of which is a P wave or a pressure wave. This can blend in with the noise a little bit easier and is marginally more difficult to detect than, of course, an S wave, which is very definite and has a definite pattern. And the second one, of course, like I just said, is an S wave. That is a surface wave. These are extremely slow, up to 3 miles a minute, which is, of course, not very fast. However, they are extremely damaging, and then followed by a series of aftershocks. So a little bit about the data set. I'm using Griot's Open EEW dataset. The data provided is sensor metadata and incoming X, Y, and Z variations on their sensors. So the metadata provided are things like location and update time. The model that I'm demonstrating for you today is learned and specialized for a specific sensor because a lot of them have different update times. And looking at it, if those individual points were coming in real time, they would update probably every 0.0332 seconds. And currently it's not set for real-time processing, but talking to the people at Griot, that's definitely a goal in the end, actually. So their sensors update the AWS dataset every 5 minutes with data. So just analyzing it, the sensor I use is sensor 6, which is located right here and is in proximity to these 3 earthquakes. Earthquakes also move longitudinally more effective, at least in terms of their P wave. And so this works out really well for sensor 6, is more data rich. For this sensor, it produces, just above 9,000 points every 5 minutes, which is extremely dense. So the initial approach was to first cross-reference 5.5 magnitude earthquakes in Mexico and produce a map that will show me where those earthquakes are relative to the sensor's latitude and longitudinal points. This was important for finding the time frame for this seismographic data I have printed right above. So the approach, so some quick requirements. I need real-time processing if I can. And it, of course, has to be able to work sequentially. So a RNN or LSTM is sort of an obvious choice. the model should be optimized for time series data and be able to work without labels. Labeling this data is extremely laborious and is not very definite. There's a discrepancy between when an earthquake starts and when those data points actually start becoming a P wave, and it's very hard to detect in such a dense data set. So the methodology. Let's first talk about our goals. We want to predict upcoming earthquakes in real time as fast as we can. I want to minimize the number of false positives and having a low reaction time, as low as possible, of course. So like I hinted at before, we're going to be utilizing an LSTM model, training it on sensor noise, and then using that to predict incoming data, and then using the loss for anomaly detection. We can, of course, test this by simulating real-time data feeding that isn't currently available. So preprocessing and processing. So the data preprocessing ended up being one of the most important parts of this project, and was extremely helpful in compressing the noise and making making P waves and S waves more distinguishable from the noise. So the input vector, of course, also has dimension constraints that the initial data doesn't. So we need to consolidate the X, Y, and Z coordinates. So my first attempt was just use basic Euclidean distance. It's my first instinct to do, taking distance from the origin. And that was relatively good, and we'll talk a little bit more about what kind of issues that posed later. The second attempt was the distance normalization of X, Y, and Z, and taking the average. So if you'll hear my phone just go off, that's actually the earthquake early warning system working effectively as it should with the simulation I provided it. So if you're using Keras, the L2 is the version of normalization you'll use. And my last attempt, I used a min-max function on X, Y, and Z coordinates and then averaged them. Very similar to the second attempt, but I wanted to emphasize outliers, and that was helpful for that. A little bit about the model. An LSTM model. Mine in particular had 3 layers: an input vector, an LSTM composed of 32 units, a dropout of about 0.7, a repeat vector, another LSTM layer, and then a final dense layer of 32 nodes. This is sort of just a simplistic look at the model, of course. LSTMs get more complicated, more granular you get. The dropout was kind of another key in this. We'll talk about this right here. The increased dropout to avoid overfitting and memorizing noise. Yes, so even though it is just noise, it's being trained on, and there's no high level correlation between one data point and the last. You can definitely still overfit. I didn't want the model to just memorize the noise, because that would produce extremely high loss values and make it very difficult to pinpoint a loss threshold to detect an anomaly, which is sort of the issue I first faced when constructing the model at first. So I had to increase the dropout rate to 0.7, which is pretty high. He set the time window to 300 data points, about 10 seconds. I wanted it to know about 10 seconds worth in order to have more of 10 seconds worth of data points and historical data in order to really detect how anomalous it is. And 10 seconds in terms of the domain of an earthquake, at least in this setting, was as optimal as I could find. It also allows for us to detect shock waves, which I think is also very important as they move a couple minutes later, or up to 30 seconds sometimes. The error function I use is a MAE. I found this to produce a more clean curve and a more and decreased loss compared to the MSE. Another big contributor here is Adagrad. Using Atom or RMS prop also didn't really allow for a large decrease in the loss rate, which is really what I was trying to capitalize on here. And the number of epochs set is to 15. Increasing the number of epochs was not necessarily useful on mostly non-correlated noise data. So here are a couple results. In the top left here, We have the first approach, using the very first data preprocessing, using a Euclidean distance, and everything else is constant. So processing Euclidean distance like this is extremely fast. It's really easy to detect once it gets above the threshold of about 0.85 right here. However, it is very susceptible to noise, and in order to compensate to get around that, you'd have to increase the threshold, which really slows down reaction time, which is what I'm trying to minimize. So after this is, sorry, and then this down here is our initial test, the first earthquake that we test on. This one doesn't have a red line, but the first data point is its initial recognition, where it first picks it up. And then this up here, sorry, I need to clarify, these are P waves. So just initial noise, and then the moderate wave that you get before an earthquake that we talked about earlier is this P wave. The reaction time on this one using the min-max preprocessing has about 11.25 seconds, a bit faster, a little bit higher threshold, which I was afraid was going to slow reaction time, but it ended up being pretty sufficient, and testing on the second earthquake down here. This on the right is what I'm also going to show you here in a second. This is what the application actually outputs. So it's easy to detect anomalies when passing 900 data points or 11,000, 8,000. However, the model can't process fast enough for that to be useful in real time. So a buffer sort of needs to be set. This is completely historical, by the way. The buffer isn't actually up to 1800. However, like I said, yes, so the buffer would need to be decreased compared to the typical testing data. And then I went to test on that with the real-time simulation. So here's a bit of a demo. So let's take a look here real quick. Yeah, so in our simulations here, every time that an earthquake is detected, it'll of course still be looking, and also trigger a warning state. It'll go out of the warning state. I actually believe that this is stopped. Oh, there we go, perfect timing. So it'll come out of the warning state as soon as it stops detecting anomalous data. As soon as it does detect it, it will trigger. So right here, we detect anomalous data when we first interact with the P wave. Right here is the first shock wave, at least the back half of one. And right here is the second shock wave that we detect. So we'll go ahead and stop this. So a few conclusions about this is the model is successful in compressing noise, detecting anomalous data in this context. In a better setting with a computer that has a GPU and a full stack software project around it with synchronization and a full notification system that's a little more robust than a text message, then this application could really be useful. It's just behind current EEW systems that I found, reacting anywhere between 5 and 10 seconds, 5.8 on average for some of them. And the model has a far lower false positive rate based on the 3 earthquakes I was able to test on. I understand that is somewhat anecdotal. However, it was the most data rich that I can make the current project. Of course, with synchronization, you would have to synchronize a buffer, make sure that synchronize buffer and data availability, which was my first approach. But I found that the overhead of synchronization was a little bit too much for this project and this scope. So anyway, thank you for your time.